Okay, let's dive right into this explainer and build a clear, reliable workflow for diagnosing and preventing sudden Oracle database performance degradation. You know this scenario. Imagine your database is just purring along smoothly, and then, completely without warning, a critical query just falls off a cliff. Performance tanks. Well, today, we're going to unpack exactly why that happens, and more importantly, how you can take control using Oracle SQL Plan Management.
We've got a great roadmap for this. We'll follow the exact diagnostic workflow of a real incident response. We'll hit the triggers, dive into diagnostics with AWR and ASH, look at SQL Plan Baselines, verify their usage, and finally talk about evolving plans. From finding that root cause to locking in a permanent fix, let's get right into it.
All right, Section 1, the triggers. Why do execution plans just regress in the first place? Let's look at the root causes.
So these are your primary culprits, the things that force the Oracle Optimizer to rethink and recalculate its paths. Schema changes or recently refreshed statistics usually lead the charge here. Take bind variable peaking, for example. It allows the optimizer to peak at values during that first hard parse to create a plan. But if your data is highly skewed, a plan that's absolutely perfect for one bind value might be a total disaster for another. Then you've got schema changes. Maybe an index was suddenly marked unusable. And of course, configuration changes to your initialization parameters can totally alter how costs are calculated across the board.
Now, this perfectly illustrates how stale statistics create a massive mismatch between estimated rows, your E rows, and actual rows, your A rows. This mismatch can rapidly shift a super efficient index range scan into a really heavy, sluggish, full table scan. Remember, the optimizer relies entirely on statistics to pick the best path. If those stats get stale, or honestly, even if they were just refreshed, the optimizer might suddenly decide your trusty index scan is no longer the way to go. If you're looking at a plan and seeing a massive discrepancy between E rows and A rows, that is a huge red flag.
And that brings us to another major trigger. As your data volume grows, you will inevitably hit what's called a tipping point. This is where the optimizer basically says, okay, those previous indents paths or nested loops, they just aren't viable anymore. It might suddenly swap you over to hash joins or full scans. If you have significant data growth or data skew and you're missing histograms, the optimizer is going to miscalculate the cost. It's really just doing the best it can with the data it can see.
Moving on to Section 2, Diagnostics with AWR and ASH. Let's see how we actually track down these bottlenecks.
Oracle actually gives us two incredibly powerful built-in tools for this, but they do serve different purposes. We use the Automatic Workload Repository, or AWR, to compare historical shifts in execution plans. It's fantastic for seeing the big picture over time. On the flip side, Active Session History, ASH, tells us exactly what transient bottlenecks a session is actively stuck on right this second during a slow execution.
So your AWR diagnostic workflow starts with pinning down the SQL_ID. If you don't have it handy, you can query the DBA Hist SQL Stat view to check historical performance metrics like elapsed time. Once you've got your SQL_ID, you check to see if the plan hash value has changed over time. If you query that view and spot multiple hash values for the exact same SQL_ID, well, congratulations, you've just confirmed a plan regression.
From there, running this specific compare period script, the AWR DRPT script, allows you to really dig in. You use it to analyze the differences in resource consumption between a fast period and a slow period. Basically, you grab a time frame where the SQL is running beautifully and compare it side by side with the degraded time frame. You're hunting for spikes in I/O or CPU and trying to spot any subtle changes in wait events or statistics that might have triggered the shift. Meanwhile, jumping over to ASH answers the immediate pressing question. Is this slow execution burning CPU, waiting on physical reads, or just blocked by locks? You can query $active session history for your specific SQL ID to find out. If the state is on CPU, your query is actively eating up processor cycles. If you spot events like DB file sequential read, your bottleneck is physical I/O. And if you're seeing NQ, TX, row lock contention, you know another session is actively blocking your SQL.
All right, Section 3, SQL Plan Baselines. Diagnosing is great, but preventing the issue entirely is way better. Let's look at how to build our defenses.
Think of SQL Plan Management, or SPM, as a very strict gatekeeper. Even if the optimizer thinks a brand new plan is the greatest thing ever, SPM forbids it from being used until it's actually proven. It's designed specifically to stop those unexpected, chaotic shifts in execution paths we just talked about. When it's enabled, it maintains a VIP list of known good, accepted plans. If the optimizer gets spooked by new stats and tries to go rogue with a new plan, SPM marks it as unaccepted and forces the database to stick to the trusted baseline. But here's the million-dollar question. How do you actually know for sure that these baselines are actively protecting your queries in production? Because a baseline is completely useless if the optimizer is somehow finding a way around it.
That takes us to Section 4, Verifying Baseline Usage. Let's check those flags.
To verify, you can query the DBA SQL Plan Baselines view. Now, a quick heads up. Baselines are linked via a signature, not a SQL ID, so you definitely have to retrieve that exact matching signature from v/SQL first. Once you're in the view, you are looking for two specific flags to be set to yes. First, enabled, meaning the optimizer is allowed to look at it, and second, accepted, meaning the plan has been officially verified as a good, performant plan.
Now, to prove the optimizer actually used it during the very last execution, you need to check the Notes section of the execution plan report. You generate this using dbmsxplan.displayCursor with the all stats last format. If you scroll all the way down to the bottom, right in the Notes section, and you see this exact phrase, SQL Plan Baseline used for this statement, you know for a fact your baseline successfully protected that query. But what if you check, and the baseline isn't being used at all? When that happens, it almost always points to an environment change. Maybe an index was suddenly made invisible or unusable, which outright breaks the accepted plan. Remember, a baseline plan physically requires certain database objects to exist and be accessible. If a DBA drops a required index or tinkers with how a table is partitioned, that baseline plan might literally become impossible to execute. When that happens, the optimizer has absolutely no choice but to find a new path. Which leads us perfectly into Section 5, Evolving New Execution Plans. What do we do when the optimizer actually comes up with something better?
Well, that's where evolution comes in. Evolution is the deliberate, highly structured process of proving that a new plan is actually more efficient than your current baseline before you trust it. SPM's main job is to block unverified plans, sure, but sometimes a new plan, like maybe switching to a hash join because a table suddenly got massive, really is legitimately faster. We just have to prove it first.
You'll actually spot these unverified plans in the baseline view. They are eligible for evolution, but currently forbidden from executing. When the optimizer generates a new execution plan that doesn't match your baseline, SPM automatically captures it and drops it into the DBA SQL Plan Baselines view. But it sets the accepted flag to no, so it's basically just sitting there, waiting in quarantine for you to verify it. And here's how you safely evolve it. By following these steps to check historical resource consumption and row estimations, you can confidently evolve a new plan. You use that AWR Compare Periods report to verify if the new plan's CPU and I/O are actually lower. You monitor ASH during a test run to ensure it's not suddenly hitting row lock contention. And critically, you check DBMS XPlan to confirm those estimated rows closely match the actual rows. Once all that checks out, you simply update the status so that accepted flips to yes.
This leaves us with a really critical question about the stability of your own systems. You now know the triggers, you know how to hunt down regressions using AWR and ASH, and you know how to lock down performance with SQL Plan Baselines. But take a second and ask yourself, if your database hit a massive data tipping point tomorrow, would it gracefully adapt, or would your critical queries fall off a cliff? Don't wait for a 3 a.m. outage to find out. Take a look at your baselines today.